Welcome friends. This video is coming after a break. I welcome you all in this new video. The topic of the video is default hinges and user-defined hinges. By hinges we mean the plastic hinges which are used in the nonlinear analysis of structures. Hinges indicate the section is no more in the elastic condition, it has gone to plastic condition. Based on the amount of force applied or moment applied, the range of plasticity will be varying in different sections. So today we want to study these two variants, the default hinges. Default hinges means the hinges which are available with the software, which are obtained from some code or from some acceptable documents. User-defined hinges are those which the user can manipulate and use it in the model to capture the realistic situation. Why this is required, we shall see in this video. Why the user-defined hinges are required, that we shall study in this video, and we shall see that under certain circumstances a user-defined hinge will be of utmost necessity. So now we are entering into the real video, and let us see what are the default hinges and what are the user-defined hinges. There are two types of hinges. One is called mechanical hinge, another is called plastic hinge. What is a mechanical hinge? You can see here in this picture. These are the hinges in the door. So as I pull the door by taking this handle, I am actually applying a force, and the distance between the force and this hinge is the lever arm. So that produces a torque and the door opens up or door closes up. So these are called mechanical hinges which cannot take any moment. Once I applied the torque, it was rotating because it could not take any moment. So these are the physical or mechanical hinges. Let us take more examples on mechanical hinge. Let us take the first diagram where it is having a fulcrum at the point A and we applied a torque at the point B. As a result, it will rotate about the point A. So it is a mechanical hinge. In the second figure, we have a three-hinged arch which has a hinge at the supports and hinge at the top. And similarly, this three-hinged arch, this unsymmetrical three-hinged arch, and a spandrel braced which has hinges at the support and hinges at the middle, and is a compound type where there are hinges at the different locations instead of the supports. Here is a practical example on the last figure. The hinges are visible at the supports and hinge at the top for a truss-like spandrel system. Now plastic hinge definition is like this. Plastic hinge is a localized zone in a structural member where plastic deformation occurs due to yielding of the material under high bending moments, shear force, torsion, etc. A plastic hinge offers highest possible resistance against the action. Now in the mechanical hinge, any action applied, the hinge could not take any moment, so it was rotating. Here it offers the highest possible resistance. For flexural member, this maximum bending moment is called plastic moment of resistance given by MP. So plastic hinges has some properties. The important characteristics are localized yielding. The plastic deformation is concentrated within a small region rather than spread over the entire member. You can idealize it to be a single point, or you can take the real length, which is called the plastic hinge length. The moment redistribution. Once a hinge forms, moments can redistribute to other sections, allowing the structure to carry additional loads. Rotation capacity. Plastic hinges possess significant rotational capacity, enabling ductile behavior and energy dissipation. Energy absorption. During earthquake, plastic hinges absorb and dissipate seismic energy through inelastic deformation. So this is where the practical use of the plastic hinges come into picture. They will dissipate the energy. So the structure will always absorb the energy from the earthquake, and only way of dissipation is through the hysteresis actions of the plastic hinges or through dampers that you have put in the system, and the material damping available in any structure. Indicator of collapse mechanism. Formation of sufficient plastic hinges converts a stable structure into a mechanism leading to collapse. Now, how does a plastic hinge form? Let us see. We have taken a cantilever system and applied a lateral force at the top of the cantilever. So as a result, when the force is large, it produces a crack at the base. Because bending moment is larger at the base, these cracks will propagate and increase in number and intensity, and finally a zone which will be fully under plastic condition. That is, it has become fully non-elastic. A part of the hinge may go inside the support, which is called strain penetration. So it is a definite length here, but for simplicity in the different software like SAP 2000 ETFs, it can be considered as a single point, which is called lumped plasticity. We have taken a simply supported beam here. So after loading, when the load increases, it may develop crack at the middle due to flexural action. Crack may increase further and further, and it may crack at the top also, and finally form a plastic hinge. Plastic hinge in steel section can be visualized through this slide. A steel I section has been taken, and we have taken a beam out of this, which is fixed at the two ends, and we applied a mid central point load. So in the beginning, when the load is less, the strain profile is elastic, and with increase of the load, the strain profile or stress profile will be increasing further, and a time will reach when the extreme fiber reaches the yield stress of the steel. There will be no further increase in the stress, because yield stress is the maximum stress possible here. And if you further apply moments here, or this load if you increase, it will go to a condition like this, where the entire top portion is under plastic condition, entire bottom portion is under plastic condition, and there is a central axis. This is called plastic neutral axis, and the top zone is under compression and bottom zone is under tension. The area of these two has to be equal, because both top and bottom have reached the yield stress, and obviously for countering the compression and tension, the area of this block and block should be equal. Now if I take the center to center distance of the blocks, this is called the lever arm. So the moment capacity or the moment of plastic moment of resistance will be given by area, half the area. This plastic neutral axis is also called equal area axis, because it divides the section into two equal halves. So that area divided by 2 into stress sigma y into lever arm, which is nothing but you can reduce it to sigma y to ZP, the plastic modulus section ZP. Let us take the case of concrete section then. In concrete section, as per Indian code, the plastic condition is given by rectangular parabolic stress block. In Euro code or in Euro code it is also similar, but in American code it is rectangular here. So this top block of the concrete is under compression, and tension is there on the bottom steel at the top, at the bottom. The full plastic resistance, moment of resistance MP is given by 1.5 multiplied by 0.3 FCK X. X is the depth of the neutral axis here. D minus 0.42x. D is the effective depth of the section from the top to the center of the bottom steel. So this indicates the plastic moment of resistance of a section. Now there is the condition I said, lumped plasticity and distributed plasticity. When I consider plasticity to be localized in a point for simplicity of the programming for analysis, it is called lumped plasticity, and in reality it is having a definite length. So if you make a rigorous software, you can perhaps incorporate this plasticity which is spread over a definite length. This is called distributed plasticity. Now let us see the difference between the mechanical hinge and the plastic hinge. Mechanical hinge, it cannot resist in a moment. Plastic hinge, it offers highest moment of resistance for a section. Mechanical hinge undergoes elastic rotation only. It undergoes plastic rotation. It does not dissipate energy through hysteresis. It dissipates a lot of energy through hysteresis. So different. Now plastic hinge length, what is this plastic hinge length? Suppose a plastic hinge is formed here which is under plastic condition. So total length we shall take is LP, which is called the plastic hinge length. Out of this, a part of this inside the support, inside the foundation maybe, inside the support, this is called strain penetration length given by LSP. So total plastic hinge length is equal to actual plastic hinge length in the member plus the strain penetration length in the support. So LP is length of plastic hinge, LSP is the strain penetration length. The curvature diagram you can see here, actual bending shown by the blue curve, and the linear to yield is given by red curve, and up to the elastic condition, the curvature is the yield curvature up to this point, and after that whatever curvature is there is the plastic curvature. So it's given 5p. For plastic hinge length calculation, formulae are available on the literature. For column or pier, LP equal to KLC plus LSP, which should be greater than or equal to 2 into LSP. K is a factor given in terms of the ultimate stress by yield stress and should be less than or equal to 0.08. LSP is depends on the yield strength of the bar of the rebar and diameter of the bar will be considered for calculation of LSP. LC, which is coming here, is the length between the critical section to point of contraflexure of the member for a pier in the height of the pier. Plastic hinge length for shear wall is given by this formula, LP equal to KHE LSP plus 0.1 LW. LW is the length of the shear wall, horizontal length, and H is the effective height of the shear wall. Now plastic hinge length in a building after you model it can appear like this. So these are all learned plasticity in single point in the beam and column. The building shown here is not healthy because a lot of hinges are formed in the columns, which it should not form. Nonlinear behavior, we have taken first diagram, figure 1, moment versus rotation. Second diagram is also moment versus rotation, but this was a curvilinear diagram and this we have idealized to a bilinear representation. A plastic hinge offers highest possible resistance as we have discussed against the action. For flexural action, this maximum bending moment is called the plastic moment of resistance MP. Now in the FEMA documents or in the ASC ACI document, you will get a diagram like this, which is showing the normalized load on one direction and the rotation or displacement in the x-axis. So A to B is elastic, B to C is plastic, and C to D is plastic, D to E is also plastic. B to C is given by the segment small a, and up to the point last, the failure point, it is given by the segment length B. Now in the hinge formation calculation in the software, we actually do not need the linear part AB. So we remove this and we get a diagram like this where it starts from the point B to C and the segments are same as earlier, AB. The segment C is the residual strength left after the system has failed, because a solid structure after failing will not go like a liquid with zero strength, so some strength will be left out. It is taken that it is about 20% strength will be left in the residual strength. So Q by Qi indicates a moment by My, M by My. My is the yield moment. So this value of this axis, this indicates the yielding condition. 1.0 is the yielding condition. Here we have taken the plastic rotation of beams from FEMA 356 for nonlinear analysis. So the parameters are like this: the tension steel compression steel ratio divided by balance steel ratio, and the shear ratio, shear force divided by width of the beam and depth of the beam, and the strength of the concrete FC dash. Now based on these two ratios, the values are given for these A, B, C segments that we have discussed, and the values of IO, LS, CP for primary members and for secondary members. Primary members take the real force in the system. Secondary members are generally non-structural members and they will not carry force. So for secondary members, the plastic rotation allowed is much higher than those in the primary members. If you look at the table, there is this C indicates compliant and NC indicates non-compliant. Compliant indicates the building has the ductile detailing as per the code, and so it is a compliant building, and these values are available like this for the segment ABC. The segment ABC in the real world, the user may not be using. Software may use. The user will be handling these IO, LS, CP values for primary members and secondary members. Furthermore, look that the IO values are not given for secondary members, indicating the IO values are common for primary members and secondary members. Now let us see the values in ACI 4117 version of the American code. So here those elementary rows, I have not shown the entire table, elementary rows are similar and the ABC lengths are also similar, meaning interpretation, and it is given IO LSCP. IO is common for primary members and secondary members, but LS is not mentioned here whether primary or secondary. You have to read the document for long time to understand what is missing, what is given. These values are actually given for only secondary members. This will lead to tremendous problem that we shall be taking up in this video. Again, remember the deformation, the post deformation curve in the normalized ordinate, vertical ordinate is like this, where segments ABC are available in the code and the point C is something like collapse prevention, point E is something like final collapse. Now let us see further. This is taken from the FEMA 356 concrete, primary and secondary given separately. IO is common for primary and secondary. In the ACI 4117 also for concrete beams, IO is common, and LS and CP are only mentioned without mentioning whether this is for primary or secondary. But if you read the document thoroughly for many pages, you will understand this is given for secondary members. So this will create problem. Now what are there? The main pages I have taken here. Immediate occupancy, how it is defined, 0.67 times deformation of the life safety, and like that. In a convoluted way, they are specifying this. This should not have been done. It could have been given directly in the table. Then, for primary components, life safety 0.7, the deformation at the point C, that is that point A, the segment A, small a. Collapse prevention for the primary, this is for primary components. Collapse prevention, deformation at the point C, that is at the same as the segment length A, but not greater than 0.75 times the point at E. Secondary components, life safety 0.75, the deformation at the point E is equal to B in our segment in the table. Collapse prevention 1.0 times, that is the actual value at the end of the segment B. So in this convoluted way, the code is given, the document is given, the things confusing the readers, which could have been easily given in the table directly. Now the SCs also describe the things. For IO, for primary and secondary it is the same point here somewhere, say. For LS, for primary it is here, for secondary it is here. For collapse prevention, this point at the point C is the for primary point for primary members, and this point at the end E is for the secondary members. Now let us make a table modifying the table of the ACI 4117, incorporating both primary and secondary members as per their dictation given in the text. I have prepared this table in a renewed way. The left hand side are the ratios, etc. Then the segments ABC are from the ACI document. IO is also from the ACI document, which is common for primary and secondary members. Now for primary members, how do I get LS and CP? It is written in the document, primary components LS equal to 0.75 delta C and CP equal to delta C. This indicates LS equal to 0.75 segment length A and CP equal to total segment length A. So I could calculate this and put this. Now for secondary members, the LS is 0.75 delta E and CP equal to delta E. So from that I could get the value of B at the end of the B6 segment, you get point E. So you could get easily the CP points, and 75% of these are the LS points for secondary members. So now let us compare these values corresponding to FEMA 356. IO is common in both the primary and secondary in both the documents. In the primary you see a little difference is there in the values. 0.02 it is 0.1880, 0.01 0.1500, a little difference like that. CP is exactly same here. LS is a bit different in the ACI document and in the FEMA 356 document. CP is again same here, whatever value, the same value repeating here in the FEMA 356. So users can use this table for making their modeling, etc. Now let us see the fallout of the plastic rotation table given in ACI document. In many software, the table of the document has been taken verbatim without considering distinction between primary and secondary members. But the plastic rotation values for different performance levels for primary members and secondary members are exactly different. As a consequence, the life safety and CP level secondary members have been passed for those of primary members. So plastic rotation values for life safety and collapse prevention for secondary members have been passed for those of primary members, creating a lot of confusions and making the structure unsafe. Primary members building designed and evaluated with the above idea are blatantly unsafe when LS and CP levels are concerned, because the plastic rotation of LS or CP level for secondary member is much higher than those of the primary members. Now, if you have designed the primary members for higher plastic rotation, your system will undergo large plastic rotation without your knowing that it has gone beyond actual LS and CP levels for the primary members. So please use the table I have given, or you can prepare your own table and use also the user-defined hinges whenever you are facing this problem in the software. Now we'll take up the case of user-defined hinge. For that purpose, we shall take the help of a SAP 2000 software. To understand what is user-defined hinge, let us take up a building designed and analyzed in SAP 2000. We'll take this display, then go to hinge results. A dialog box will appear. Here you select a hinge that you want. That hinge that you want to make user defined. These are default hinges available. You take up the default hinge and you can now make it user defined. Hinge properties name you can change here. This name is written. For the time being it is not highlighted because the system is locked. So it is a moment hinge. You go to modify hinge and you see the things. So this is the nonlinear force deformation moment rotation curve without including the elastic part as we discussed earlier. And these are the different points A, B, C, D, E as given in the FEMA or in the SEI document. Here it is given the moment scale factor for positive steel and negative steel. The values are different. This is in kilonewton meter. This you can say the yield moments of the section. And rotation scale factor is 1. So whatever rotation values are given here are unscaled. So you can see here the immediate occupancy values are given. So if needed, you can change it to your user defined values. That is, if you are not satisfied with the values given in the software, then you can modify it. Similarly, life safety, immediate occupancy is of course not changed in the table, so there will be no discrepancy about this. But life safety and collapse prevention, the values may be corresponding to the secondary components which you want to make corresponding to primary components. So you can edit this and change and then save this, and the name you have given, that becomes the new user defined hinge which you can attach to different members where you want to attach it. Friends, you have come to the end of the video. If you have found the video useful and informative, please like and share it. If you have not already subscribed the channel, please subscribe the channel. And you can put your comments and queries in the comment box. I shall be glad to answer those. Thank you.